Every second that passes changes everything. Imagine waking up. The sunlight filters through the curtains, casting a soft glow across your room. You stretch, blink, and glance at your clock. The hands are ticking, quietly marking the passage of something we rarely think about: time. We live within it, yet it eludes us at every turn. Seconds tick by, minutes fade into hours, and days slip into memory like sand slipping through our fingers. You grab your phone, check your calendar, and glance at your to-do list. Every event, every meeting, every deadline is bound by a force so ordinary yet so profound: time. We organize our lives around it, try to manage it, and yet, like a whisper in the wind, we can never truly grasp it. But what is time? What is this invisible force that governs our every moment? Is it merely the ticking of a clock, or does it run deeper into the very fabric of the universe? In this documentary, we'll explore on a journey through the timeline of existence itself. From this very moment you are living, all the way back to the origins of everything and further beyond the present to the mysterious future that awaits us all. Let's start with a question. What is now? Right now, in this instant, what do you feel? You're experiencing the present. You're aware of yourself, the room around you, and the sensations of being alive in this particular moment. But the now is elusive. As soon as we perceive the present, it's already slipping into the past. Every breath you take, every word you hear, it's all immediately behind you. We chase the present, but we're always just a step too late. The truth is, the present moment is a moving target. From a scientific perspective, now is an ever-shifting boundary between what's already happened and what's yet to come. But why does it feel so real? Why do we feel grounded in this fleeting now? In the universe, time isn't just a subjective experience, it's a one-way street. Time flows forward, and we call this concept the arrow of time. It's this one-directional flow that defines our experience of reality. From the cradle to the grave, from the Big Bang to the ultimate fate of the universe, time marches on, never looking back. Let's consider this. Why doesn't time flow backward? Why can't we unspool moments and return to them like rewinding a tape? The answer lies deep within the laws of physics, and the key concept is entropy. The second law of thermodynamics tells us that in a closed system, entropy or disorder always increases. Imagine breaking an egg. The yolk and white scatter in a chaotic mess. But no matter how hard you try, you can't unbreak that egg and return it to its original, pristine state. This gradual shift from order to disorder is what gives time its forward direction. It's why you remember the past, but not the future. In the universe, everything moves toward greater entropy, and that's why time for us feels like a river, flowing steadily in one direction. But the arrow of time is more than just a principle of physics. It's woven into the fabric of our lives. It's why we grow older, why stars burn and eventually die, and why we can't return to moments long gone. Our existence is defined by this one-way flow, carrying us from one moment to the next, never allowing us to pause, rewind, or relive the past. What's fascinating is how time shapes every experience, and yet time itself remains one of the greatest mysteries. Ancient philosophers pondered its nature, and modern scientists have developed theories that stretch our understanding of reality. But no matter how much we learn, time remains in many ways a mystery. In this documentary, we will discuss the mysteries of time, traveling back through history to when our universe first exploded into being and forward into the distant, uncertain future. So, what exactly is time? Physicists define it as a dimension, much like space. But unlike the spatial dimensions, time has an intrinsic direction. It's a way to measure the intervals between events. Time is what separates before from after, and it's intimately tied to the fabric of the universe. But time is also something more than a cold scientific concept. For us, it's deeply personal. Time is the framework of our lives, the constant rhythm in the background of everything we do. It's measured in the beats of our hearts, the rotation of the earth, and the pulse of the cosmos. Time governs everything, from the rise and fall of civilizations to the life and death of stars. Time to us feels constant, but it's not. For example, Einstein's theory of relativity tells us that time isn't the same everywhere. Time moves faster at the top of a mountain than it does at sea level. Time slows down the closer you get to a black hole. In the vastness of space, time stretches and warps, bending reality itself. And yet in our daily lives we rarely think about this. We wake up, check the time, rush through our day, and rarely stop to consider, what is time, where does it come from, and where does it lead? In this journey, we'll seek answers. We'll travel to the very beginning of time, to the birth of the universe in the fiery explosion of the Big Bang. We'll watch as stars are born and galaxies form. We'll witness the rise of life on Earth and the development of human civilization, all through the lens of time. Then we'll venture beyond the present into the future, exploring the ultimate fate of time itself. What will happen to the universe when entropy reaches its peak? Will time, as we know it, come to an end? But before we look back or peer forward, we need to ground ourselves in this moment, in the fleeting present. Because, after all, the only time we truly experience is now. As we delve into the nature of time, we'll explore the threads of history, science, and philosophy. The next stop in our journey? The past, where time, space, and the universe itself began. So, as you sit here now, surrounded by the familiar sights and sounds of your life, pause for a moment. Take a breath. In this documentary, we'll explore the story of time, from the microscopic ticks of the atomic clock to the incomprehensible stretches of cosmic time. But through it all, remember, every story, every moment, every life is shaped by time, and it all begins with now. Let's begin by looking at time as we humans experience it. Every person on this planet is tethered to the flow of time, though our relationship with it varies depending on who we are, where we are, and what we're doing. Imagine this. It's a Monday morning and you're rushing through the crowded streets of a bustling city. The clock is ticking down to 9 a.m. and your entire day feels like a race against time. Meetings, deadlines, the next appointment always looming ahead. Now, contrast that with a lazy afternoon in the countryside where time seems to move slower, with nothing more pressing than the slow sway of the trees in the breeze. Two vastly different experiences, yet both unfolding within the same dimension of time. What's happening here is something remarkable. Even though time is constant, each second lasts exactly as long as the one before, our experience of it is anything but. In moments of stress, time feels like it speeds up, but when we're bored or relaxed, it seems to slow down. This is the essence of the human experience of time, subjective, fluid, and ever-changing. Why does time feel so different depending on what we're doing? The answer lies in our perception of time. a psychological process deeply influenced by our environment, emotions, and state of mind. For instance, attention and emotional states like stress or joy can dramatically alter how we perceive time. Dopamine, a neurotransmitter involved in focus and reward, also plays a significant role. Higher dopamine levels, often linked to high engagement or excitement, make time feel like it's speeding up, while lower dopamine can make time drag. In the fast-paced life of a city filled with distractions, commitments, and constant stimulation, we often feel like time is slipping away. Days blur into weeks, and before we know it, months have passed. Psychologists refer to this as time pressure, where the brain feels overwhelmed by the number of tasks competing for attention, making time seem to race ahead. On the other hand, in slower-paced environments like rural areas, the lack of constant stimuli and deadlines gives us the impression that time stretches out. Hours spent walking through nature or sitting quietly feel longer, more substantial. Time perception is also affected by age. Children often experience time more slowly, while adults, especially those with routine-filled lives, find that time speeds up as they age. Neuroscientists have studied this phenomenon. They've found that our brains don't process time in a straightforward, clock-like manner. Instead, time perception is influenced by how much attention we're paying to our surroundings. The more information the brain has to process, the slower time seems to go. In addition, recent studies show that our perception of time is connected to dopamine levels and activity in areas of the brain like the prefrontal cortex. But there's more to our experience of time than just perception. Inside each of us, there's a complex system of internal clocks, biological rhythms that govern everything from when we wake up to how we sleep. These rhythms are known as circadian rhythms, and they're synced to the 24-hour cycle of the Earth's rotation. These rhythms are influenced by zeitgebers, external cues like light, which help keep our internal clocks aligned with the natural world. The human body runs on a schedule. At dawn, the release of cortisol wakes us up. As the day goes on, various hormones and chemicals regulate our alertness, hunger, and energy levels. By evening, melatonin starts to flood our system, preparing us for sleep. These rhythms are controlled by a small part of the brain called the suprachiasmatic nucleus, our internal master clock. Disruptions to this biological clock, such as jet lag or shift work, can profoundly affect our perception of time. When our internal clocks are out of sync with the natural world, time can feel disorienting. This mismatch between biological time and environmental time can lead to feelings of fatigue, stress, and even health problems. We've now seen how humans experience time, but is this perception the same as how the universe itself measures time? Here's where we encounter a fascinating distinction between subjective time, the way we feel time, and objective time, the way the universe actually flows. In our everyday lives, time seems straightforward. We look at clocks, mark the passing of hours and days, and feel as though the world runs on a constant rhythm. But in the world of physics, time is far more complicated. Einstein's theory of relativity revolutionized our understanding of time. Before Einstein, time was thought to be absolute, a constant universal flow that ticked at the same rate for everyone. But in 1905, Einstein showed that time is relative. It can stretch, contract, and warp, depending on how fast you're moving or how close you are to a massive object. This leads to a stunning realization. Time is not the same for everyone, everywhere. For example, if you're standing still on Earth, time flows differently than it would if you were travelling at nearly the speed of light in space. Similarly, time flows more slowly near a black hole due to its immense gravitational pull. This idea of time dilation is one of the strangest and most beautiful concepts in physics. Time isn't the uniform ticking clock we once thought it was. It's fluid, malleable, and deeply connected to the fabric of space itself. But let's return to the present. What exactly is now? It's easy to think of now as a single moment we're living in, the thin line between the past and the future. But as we've seen, this isn't quite accurate. Yet for us, now feels unique. We experience life moment by moment, always in the present. Philosophers and physicists have long debated this idea, and two competing views have emerged: presentism and eternalism. Presentism is the belief that only the present is real. According to this view, the past no longer exists, and the future is just a possibility. All that's real is this fleeting moment. On the other hand, eternalism suggests that the past, present and future are equally real. In this view, time is like a vast landscape stretching in every direction. While we may only experience one moment at a time, every moment exists simultaneously. From an eternalist perspective, time doesn't flow in the way we experience it. Instead, all of time exists at once, and our perception of its flow is simply an illusion. Which view is correct? That remains one of the great mysteries of philosophy and physics. While eternalism aligns more closely with the theory of relativity and the four-dimensional spacetime model, presentism captures our human experience of time. As you sit here watching this documentary, it's hard to deny that the present feels special. Now that we've explored what now means, let's take it a step further. Imagine two people, one standing on Earth and another travelling through space at nearly the speed of light. You might think they'd experience time in the same way, but in reality, their experience of now is completely different. This is due to a concept known as the relativity of simultaneity. According to Einstein's theory of relativity, events that appear to happen at the same time for one observer may happen at different times for another observer moving at a different speed or in a different gravitational field. Let's break this down with an example. Imagine a lightning strike hitting two ends of a train simultaneously. For a person standing on the ground, the strikes happen at the same time. But for someone inside the train, moving towards one of the strikes, the lightning that's ahead of them appears to hit first. This isn't an illusion. Time itself is behaving differently for the person on the train compared to the person on the ground. What does this mean? Quite simply, the idea of a universal now doesn't exist. What's now for you may not be now for someone else in a different part of the universe, moving at a different speed. Time, like space, is relative. It bends, warps, and shifts depending on your perspective. So where does this leave us? The present moment feels real to us, but science tells us that time is more flexible, more complex than our everyday experience. Our brains perceive time in ways shaped by our biology, our environment, and even our mental state. Meanwhile, the universe itself measures time on a grander, more abstract scale, one where now is not as absolute as we might think. Let's journey back to a time when the concept of tracking hours, days, or years was not yet part of human existence. Early civilizations relied on natural rhythms, such as sunrises, sunsets and lunar phases, to mark the passage of time. As societies grew more complex, the need for a more precise system of timekeeping became essential. Long before digital watches and atomic clocks, humans developed remarkably innovative techniques to keep track of time. One of the earliest methods was the sundial, used by the Egyptians as early as 1500 BCE. Sundials measured the movement of shadows cast by the sun to indicate the time of day. Simple in concept, yet brilliant in application, sundials were crucial for managing daily activities. That's where water clocks and candle clocks came into play. In ancient China and the Middle East, water clocks measured time by the consistent flow of water from one container to another. Candle clocks, on the other hand, measured time by the slow burning of a candle. These ingenious methods helped humans keep track of time during the night or on cloudy days. The evolution of calendars marked another significant leap in timekeeping. Ancient civilizations, such as the Maya and Egyptians, developed complex systems based on astronomical observations. For example, the Mayan calendar, which tracked time through interlocking cycles, is a testament to their advanced understanding of astronomy. As societies evolved, the need for more precise timekeeping grew. The mechanical clock revolutionized human history. The first mechanical clocks appeared in Europe in the 13th century, using gears and escapements to maintain accurate time. Unlike sundials and water clocks, mechanical clocks could tick away reliably day and night, independent of natural phenomena. By the 17th century, pendulum clocks, pioneered by Dutch scientist Christiaan Huygens, became the most accurate timekeeping devices of their era. These clocks were so precise that they lost only a few seconds per day, a remarkable achievement for that time. The pinnacle of timekeeping accuracy came in the 20th century with the invention of the atomic clock. Atomic clocks measure time based on the vibrations of atoms, typically cesium atoms. They are so precise that they can keep time to within 1 second over 100 million years. Atomic clocks are essential for modern life. Technologies like GPS, satellite communications, and the synchronization of global time all rely on their precision. With global trade and communication expanding, a standardized timekeeping system became necessary. Greenwich Mean Time, or GMT, was established in 1884 at the International Meridian Conference, choosing Greenwich, England as the prime meridian, 0 degrees longitude. GMT became the reference point for time zones around the world, allowing people across the globe to synchronize their activities based on a unified clock. Time, however, isn't always predictable. The Earth's rotation is not perfectly consistent and gradually slows down due to gravitational forces. To keep our clocks aligned with Earth's actual rotation, leap seconds were introduced in 1972. These extra seconds are occasionally added to Coordinated Universal Time, or UTC, to ensure that our timekeeping systems stay synchronized with Earth's changing rotation. Although leap seconds are still in use today, there have been discussions about potentially phasing them out. Today, UTC is the global standard for time, ensuring that every transaction, broadcast and satellite transmission happens precisely when it should. Now that we've established how humanity learned to track time, let's explore our understanding of its nature. For centuries, time was believed to be absolute, flowing uniformly for everyone. Sir Isaac Newton solidified this view in the 17th century with his laws of motion and gravity. Newton described the universe as a giant clockwork machine, operating according to fixed laws. Time, in this framework, was an ever-ticking constant, unaffected by motion or location. This concept of absolute time laid the foundation for classical mechanics and was widely accepted for over 2 centuries. Newton's idea, though elegant, wasn't immune to challenge. As our understanding of the universe deepened, it became clear that time wasn't as constant as Newton had imagined. Enter Albert Einstein, who in the early 20th century introduced his theory of relativity, fundamentally altering our perception of time and space. In special relativity, time is no longer absolute. It is relative, dependent on the observer's motion. The faster you move, the slower time passes for you compared to someone who is stationary. This phenomenon, known as time dilation, is best illustrated with an analogy. Imagine you're aboard a train travelling close to the speed of light. Inside the train, time seems to tick forward as usual. You look at your watch and everything feels normal. But for someone watching from the ground, your watch would appear to be moving incredibly slowly. Time for you is literally stretching out because of the high speed at which you're travelling. Einstein's theory goes even further in general relativity, where gravity is introduced as a warping of spacetime itself. Massive objects like planets and stars bend spacetime, causing time to move more slowly the closer you are to them. This is why time runs slightly slower on Earth's surface compared to higher altitudes or space. Einstein's insights revealed that time isn't an absolute uniform entity flowing through the universe. Instead, it's a dynamic force, malleable and influenced by motion and gravity. This new understanding of time opened up possibilities for concepts like time travel and wormholes. As we move from ancient timekeeping methods to modern physics, it's clear that our perception of time has evolved. From sundials and mechanical clocks to the realization that time itself can stretch and bend, we now understand that time is a malleable force intertwined with the very fabric of the universe. Through the discoveries of Newton and Einstein, we have come to see time not as a rigid framework, but as a living entity, one that flows differently for each of us depending on where we are and how fast we're moving. The story of time is far from over, and as we continue to explore the mysteries of space and time, who knows what new revelations lie ahead? Imagine standing on the shore, gazing out over the ocean. The waves rise and fall rhythmically, an endless cycle that stretches far beyond your lifetime. Now imagine trying to fathom not just the scale of your life, but of the Earth itself, with its history spanning billions of years. This is the concept of deep time, a timescale so vast that it transcends human experience, compressing billions of years into what geologists call geological periods. Earth is about 4.54 billion years old, a staggering number that stretches far beyond our ordinary sense of time. To give that number meaning, let's imagine compressing Earth's entire history into a single calendar year. If Earth were born on January 1st, the first forms of life would appear sometime in March. Dinosaurs wouldn't roam until mid-December, and modern humans would only show up in the final seconds of December 31st. This analogy reveals the mind-boggling vastness of Earth's history, where human existence represents just a blink of an eye. The idea of deep time was first proposed by James Hutton, an 18th century Scottish geologist, who observed that Earth's geological processes, like the slow erosion of rocks and the formation of sedimentary layers, occurred over unimaginably long periods. Hutton's observations laid the groundwork for the field of geology, which studies Earth's history written in the layers of rock beneath our feet. Around 4.6 billion years ago, Earth formed from the dust and gas left over from the birth of the Sun. Over millions of years, gravity pulled these particles together, creating a hot, molten planet. The young Earth was a chaotic place, constantly bombarded by asteroids and comets. But slowly, as the planet cooled, oceans formed and a thin crust began to solidify. The earliest evidence of life on Earth dates back roughly 3.7 billion years, when microscopic organisms called prokaryotes appeared. These simple, single-celled organisms were the first to harness energy from the sun through a process known as photosynthesis. The oxygen produced by photosynthetic bacteria began to accumulate in the atmosphere, leading to one of the most significant events in Earth's history, the Great Oxygenation Event, which dramatically altered the planet's atmosphere and triggered a mass extinction of anaerobic organisms. It has been punctuated by catastrophic events that have radically altered the course of life. The most well-known of these are the mass extinction events. Perhaps the most famous is the Cretaceous-Paleogene extinction, which wiped out the dinosaurs 66 million years ago, likely caused by a massive asteroid impact that threw dust and debris into the atmosphere, blocking sunlight and disrupting global ecosystems. But long before the dinosaurs ruled the Earth, another extinction event, the Permian-Triassic extinction, occurred about 252 million years ago. This event, also known as the Great Dying, wiped out nearly 96% of all marine species and 70% of land species. While the cause is still debated, scientists believe massive volcanic eruptions in what is now Siberia released enormous amounts of carbon dioxide, triggering runaway climate change and ocean acidification. Understanding these ancient events helps us appreciate the resilience and fragility of life on Earth. Every era in geological history tells a story of adaptation, extinction, and the evolution of new species, a story written in the rocks, fossils, and layers of sediment that geologists study today. As we zoom out from Earth's history and begin to consider time on a cosmic scale, we encounter an entirely different rhythm, the cosmic clock. The universe itself is about 13.8 billion years old, and like Earth's history, it is filled with cycles of creation and destruction. One of the most fascinating examples of these cycles is the life cycle of stars. Stars, like living organisms, are born, grow, and eventually die. They begin as vast clouds of gas and dust called nebulae. Over time, gravity pulls the material together, and as the pressure and temperature rise, nuclear fusion begins in the core, igniting the star. These stars can live for millions to billions of years, depending on their size. Smaller stars, like our Sun, burn slowly and steadily, while massive stars burn bright but live shorter lives. The end of a star's life depends on its mass. A star like the Sun will eventually swell into a red giant, shedding its outer layers and leaving behind a small, dense core known as a white dwarf. This will be the fate of our Sun, though not for another 5 billion years. For much more massive stars, however, the end is far more dramatic. These stars die in spectacular explosions called supernovae, which can outshine entire galaxies for a brief period. After the explosion, the remaining core can collapse into a neutron star, or if the star was massive enough, a black hole, an object so dense that not even light can escape its gravitational pull. These stellar deaths play a crucial role in the universe because the heavy elements formed in these explosions are scattered across space, eventually becoming part of new stars, planets, and even life itself. In fact, the very atoms that make up your body were forged in the heart of a dying star billions of years ago, a reminder that we are, quite literally, made of stardust. Stars don't exist in isolation. They are part of vast collections of stars, gas, dust and dark matter known as galaxies. Our home galaxy, the Milky Way, formed about 13.6 billion years ago, not long after the universe itself. Like all galaxies, the Milky Way is in constant motion, rotating as its stars orbit the galactic center, which is home to a supermassive black hole. Galaxies are thought to form through the gravitational collapse of gas and dark matter in the early universe. Over billions of years, galaxies grow by merging with other galaxies, a process that continues today. In fact, the Milky Way is on a collision course with our nearest galactic neighbor, the Andromeda Galaxy. In about 4.5 billion years, the two galaxies will merge, forming a new larger galaxy. The study of galaxies has revealed that they too have life cycles. Some galaxies are still actively forming new stars, while others have become dead, meaning they have exhausted their supply of gas and can no longer create new stars. The Hubble Space Telescope and other observatories have allowed us to peer back in time, observing galaxies as they appeared billions of years ago, giving us a glimpse into the early universe and the process of galaxy formation. Understanding the history of our galaxy and the broader universe gives us a sense of the vastness of cosmic time. While our lives are fleeting, the stars, galaxies, and the universe itself operate on timescales that stretch far beyond human comprehension. At the intersection of cosmic time and human perception lies one of the most mind-bending concepts in modern physics, relativity. Proposed by Albert Einstein in the early 20th century, the theory of relativity fundamentally changed our understanding of time and space. One of the most intriguing aspects of relativity is the idea that time does not move at the same rate for everyone. In fact, time is relative, meaning it can speed up or slow down depending on certain conditions, like velocity or proximity to a massive object. This phenomenon is known as gravitational time dilation. Imagine you are standing on Earth while your friend is near a black hole. Black holes, with their immense gravity, warp the fabric of space-time. According to Einstein's general theory of relativity, time moves more slowly in stronger gravitational fields. So while you experience time as usual on Earth, your friend near the black hole would experience time much more slowly. If they were to return to Earth after spending a short time near the black hole, they would find that many years had passed for you, while only a few moments had passed for them. This idea, though counterintuitive, has been confirmed by numerous experiments. For example, atomic clocks placed at different altitudes run at slightly different rates, with clocks at higher altitudes where the gravitational pull is weaker, running slightly faster than those at sea level. GPS satellites also experience time dilation, and engineers account for this difference to ensure they provide accurate location data. Another fascinating consequence of relativity is the twin paradox, a thought experiment that illustrates how time slows down as an object approaches the speed of light. The paradox goes like this. Imagine two twins, one of whom stays on Earth, while the other travels through space at nearly the speed of light. When the traveling twin returns to Earth, they will have aged much more slowly than their sibling who remained on the planet. This paradox arises from Einstein's special theory of relativity, which states that as an object's speed increases, time slows down for that object relative to a stationary observer. This effect becomes more pronounced as the object approaches the speed of light. Though it might sound like science fiction, time dilation has been confirmed by experiments involving particles traveling at high speeds. For instance, particles called muons are created in the upper atmosphere and travel toward Earth at nearly the speed of light. Due to time dilation, these particles survive much longer than they would if they were stationary, allowing them to reach the surface of the planet before decaying. From the formation of the Earth to the vast cycles of stellar evolution, from the slow dance of galaxies to the mind-bending implications of relativity, our understanding of time has expanded beyond anything our ancestors could have imagined. The concept of time, whether geological, cosmic or relative, continues to challenge our perception of reality. In this chapter, we've journeyed through deep time, considering the geological history of our planet, the life cycle of stars, and the evolution of galaxies. We've also explored how relativity has reshaped our understanding of time, revealing that time is not an absolute fixed entity, but a dynamic force that can stretch, bend, and slow, depending on your location in the universe. As we continue to explore the mysteries of time, one thing remains clear. Whether measured in seconds, years, or eons, time is the fabric upon which the universe is built. It governs everything, from the smallest particle to the largest galaxy, and understanding it is key to unlocking the secrets of the cosmos. As we examine time on a grand scale, we begin to question its origins. Where does time itself come from? Is there a before time? To answer these questions, we must journey back to the most critical moment in the history of the universe, the Big Bang, which occurred approximately 13.8 billion years ago. The Big Bang is often described as the moment when the universe exploded into existence. But contrary to popular imagery, it wasn't an explosion in space. It was an explosion of space itself. More precisely, it was the moment when space, time, matter, and energy were created. Before this event, concepts like before or after didn't exist in the way we understand them. In fact, time itself began with the Big Bang, meaning there was no before in any meaningful sense. In the moments leading up to the Big Bang, everything was compressed into a single point of infinite density, a state known as a singularity. This singularity defies the laws of physics as we currently understand them. At this point, the gravitational pull was so immense that even the fundamental forces of nature, such as electromagnetism and gravity, were indistinguishable from one another. Temperatures were incredibly high, and the universe, if it could be called that, was unimaginably small. The period immediately following the Big Bang is referred to as the Planck Epoch, named after physicist Max Planck. This epoch lasted only a fraction of a second, approximately 10 to the power of minus 43 seconds. Yet it set the stage for the entire universe. During the Planck Epoch, quantum mechanics and general relativity, the two cornerstones of modern physics, were unified. However, we still lack a complete theory of quantum gravity to describe how these forces interacted during this period. The physical laws that govern our everyday reality simply don't apply here, making this period one of the most elusive and mysterious moments in the universe's history. To understand the origins of time, we must think of time as more than just a series of moments ticking away on a clock. Instead, we need to understand it as part of a larger framework, spacetime. Spacetime, as described by Einstein's theory of relativity, is a four-dimensional fabric that weaves together the three dimensions of space with time. Imagine this fabric as a flexible, stretchable sheet. In this analogy, the Big Bang is the moment when this fabric was first stretched, marking the beginning of both time and space. Before the Big Bang, there was no space-time fabric. No before, no after, no space, and no time. The concept of time as we know it could not exist because time itself had not yet been created. The singularity, where all matter and energy were compressed, existed outside the boundaries of time. It was only with the Big Bang that time began to flow. This is why scientists say that asking what came before the Big Bang is like asking what's north of the North Pole. It's a meaningless question because the concept of before didn't exist until time itself began. As the universe expanded from the singularity, space-time unfolded. And with it came the arrow of time, a one-way progression from past to future. The Planck Epoch marks the beginning of this journey, though it was far too brief for us to fully understand its intricacies. What we do know is that during this time, all four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were unified into a single force. As the universe cooled and expanded, these forces began to separate, setting the stage for the formation of matter and energy as we know them today. Let's pause for a moment and try to grasp the nature of space-time. Imagine space-time as a stretchy fabric that bends and warps in the presence of mass and energy. This analogy helps explain how gravity works, according to Einstein's theory of general relativity. Massive objects, like stars and planets, create indentations in the fabric of space-time, and other objects move along these curves, which we perceive as the force of gravity. The Big Bang wasn't just the beginning of time, it was also the beginning of space. The expansion of the universe can be visualized as the stretching of this space-time fabric. However, it's crucial to understand that the Big Bang didn't happen in space. Space itself was created as the universe expanded. The universe is not expanding into something. Rather, it's creating more space as it grows. In the context of space-time, time is not an independent entity that flows separately from space. Instead, time is deeply intertwined with space, and the two must be understood as a single, unified entity. This is why physicists often speak of the fabric of space-time, emphasizing that time cannot exist without space, and vice versa. As the universe expanded after the Big Bang, space and time evolved together, forever linked by the fabric of space-time. In the first few moments, the universe was a hot, dense plasma of particles. It was so hot that atoms couldn't yet form, because any attempt to bond was immediately broken by high-energy photons. This period, known as the opaque era, lasted for about 380,000 years. As the universe continued to expand and cool, it eventually reached a point where the temperature dropped enough for protons and electrons to combine and form neutral hydrogen atoms. This moment, called recombination, was a turning point in the universe's history because it allowed light to travel freely for the first time. The universe became transparent, and the light released at that moment still travels through space today. We observe this light as the cosmic microwave background radiation, often referred to as the fossil of time, because it provides a snapshot of the universe as it existed just 380,000 years after the Big Bang. It is a remnant of the heat from the early universe, now cooled to just 2.7 degrees above absolute zero. By studying the tiny fluctuations in the cosmic microwave background, scientists have been able to map the early structure of the universe and trace its evolution from a uniform plasma to the diverse, structured cosmos we see today. The CMB also holds clues about how time and space have evolved together. The small variations in temperature that we observe in the CMB correspond to regions of slightly different densities in the early universe. Over billions of years, these regions of higher density would collapse under their own gravity to form galaxies, stars, and planets. In this way, the evolution of space and time is inextricably linked to the formation of structure in the universe. The Big Bang theory explains much about the origin of the universe, but it leaves one significant question unanswered. Why is the universe so uniform on large scales? Why do regions of the universe that are billions of light years apart appear to have the same temperature and structure, even though they are too far apart to have ever exchanged information or energy? The answer to this puzzle lies in the theory of cosmic inflation. Inflation proposes that in the first tiny fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing from the size of a subatomic particle to something much larger in an instant. This rapid expansion smoothed out any irregularities in the early universe, creating the large-scale uniformity we observe today. Cosmic inflation lasted for an incredibly brief period, about 10 to the minus 32 seconds, but it had profound consequences for the evolution of the universe. During this time, quantum fluctuations, tiny random variations in energy, were stretched to cosmic scales, seeding the formation of galaxies, stars, and planets. These quantum fluctuations also played a role in shaping the distribution of matter in the universe, leading to the clumping of matter that would eventually form galaxies. One of the most intriguing questions about the universe is why time flows in one direction, from past to future, when the laws of physics allow for the possibility of time flowing in either direction. The answer lies in the concept of entropy. Entropy is a measure of disorder or randomness in a system. According to the second law of thermodynamics, the total entropy of a closed system can never decrease. It can only stay the same or increase. This law gives rise to what we call the arrow of time, the one-way progression from order to disorder that defines our experience of time. At the moment of the Big Bang, the universe began in a state of extremely low entropy. This means that the early universe was highly ordered, with matter and energy distributed uniformly across space. As the universe expanded, its entropy increased, leading to the formation of stars, galaxies, and the complex structures we observe today. The arrow of time is closely linked to the expansion of the universe. As space expands, entropy increases, and time marches forward. This explains why we can remember the past but not the future. Events unfold in a way that increases the overall disorder of the universe. The increase in entropy also explains why certain processes, like mixing cream into coffee or breaking an egg, are irreversible. Once entropy has increased, there is no way to reverse the process and restore the system to its original low entropy state. In the context of the universe as a whole, the arrow of time points in the direction of increasing entropy. This means that the universe will continue to evolve toward greater disorder, eventually reaching a state of maximum entropy, where all energy is evenly distributed, and no further work can be done. This final state is sometimes referred to as the heat death of the universe, a time when all processes will cease, and the universe will exist in a state of eternal equilibrium. In this chapter, we have traced the origins of time back to the moment of the Big Bang, a singularity that gave birth to space, time, matter, and energy. We explored the concept of spacetime, where time is not a separate entity but a dimension intricately connected to space, forming the very fabric of the universe. From the first moments of cosmic inflation to the present-day universe filled with galaxies, stars, and planets, we've seen how time and space have evolved together. We've also delved into the role of entropy in defining the arrow of time, explaining why time moves forward and why we experience the past but not the future. The universe began with low entropy, and, over billions of years, it has moved toward increasing disorder, a process that will continue as the universe expands into the future. As we continue our journey through the cosmos, we will confront even more profound questions about the nature of time and the universe's ultimate fate. What will happen when entropy reaches its maximum? Will time come to an end, or will new laws of physics emerge to govern the universe in its final state? These questions lie at the heart of our exploration of time, as we seek to understand not only where we came from, but also where we are headed. Time, like the universe itself, is a vast and ever-evolving mystery, one that we're only just beginning to understand. As we stand at the precipice of our understanding of the universe, one of the most compelling questions we face is, what lies ahead? We've delved into the origins of time and the vastness of deep time. But now, let's turn our attention to the distant future, the future of time itself. What will become of the universe? Will time continue indefinitely, or will it meet an end? In this chapter, we explore the potential fates of the universe and how they might shape the very concept of time. To envision the future of time, we must first understand the fate of the universe. Currently, the universe is expanding, a fact discovered in the early 20th century by astronomer Edwin Hubble. But this expansion isn't slowing down, in fact it's accelerating. This acceleration is driven by a mysterious force we call dark energy. Dark energy remains one of the most significant enigmas in modern physics, as it makes up roughly 68% of the total energy in the universe, yet we know almost nothing about its nature. In the 1990s, observations of distant supernovae revealed that the expansion of the universe was not only continuing, but also speeding up. This discovery turned the field of cosmology on its head. It meant that the universe wasn't just coasting along. It was being pushed outward by something unseen. Dark energy seems to be stretching the fabric of space-time itself, driving galaxies apart at an ever-increasing rate. The consequences of this accelerated expansion are profound. If dark energy continues to dominate the universe's fate, it will determine how time unfolds on the largest scales. There are three main scenarios that cosmologists consider when thinking about the ultimate fate of the universe: the Big Freeze, the Big Crunch, and the Big Rip. Each scenario offers a different vision of how the universe might end, and what that means for time itself. One of the most widely accepted scenarios for the future of the universe is the Big Freeze. In this scenario, the universe continues to expand indefinitely, driven by dark energy. As space expands, galaxies move farther apart, and the distances between stars grow so vast that they become isolated in the cosmic void. Over billions and trillions of years, stars will exhaust their nuclear fuel, burning out one by one. The once vibrant universe will grow cold and dark as the lights of the cosmos gradually flicker out. The Big Freeze is often described as the heat death of the universe. This is because as the universe expands and cools, it will eventually reach a state of maximum entropy, a condition where all energy is evenly distributed and no work can be done. In this state, time as we experience it will lose much of its meaning. Without processes that change, like stars shining, planets orbiting, or life evolving, there is no way to mark the passage of time. The universe will settle into an eternal, unchanging state of cold darkness. But even in the farthest reaches of the future, the universe will still have some remnants. Black holes, the corpses of massive stars, will continue to exist for eons, slowly evaporating via a process called Hawking radiation. Eventually, these black holes will vanish too, leaving behind nothing but a sea of particles drifting through an empty cosmos. From the perspective of time, the Big Freeze represents a future where time stretches into infinity but becomes meaningless in the absence of events to measure it. With no more heat, no more energy gradients, and no more processes, time as a concept might become indistinguishable from eternity. While the Big Freeze suggests a universe that expands forever, the opposite scenario, the Big Crunch, suggests a more cyclical fate. The Big Crunch is the idea that the universe's expansion might one day reverse. Instead of flying apart, galaxies would begin to move closer together, eventually collapsing back into a singularity, similar to the state from which the universe emerged during the Big Bang. This concept hinges on the amount of matter and energy in the universe. If the gravitational pull of all the matter in the universe is strong enough to overcome the force of expansion, then the universe could stop expanding and begin to contract. As galaxies collide and merge, temperatures would rise and the universe would become denser and hotter, eventually collapsing into a super-hot, super-dense state, essentially a reverse Big Bang. In a Big Crunch scenario, time as we know it would come to a dramatic end. As the universe contracts, space-time itself would begin to fold in on itself. Time, which began with the expansion of space-time at the Big Bang, would effectively cease to exist in the same way as the universe collapses. If the universe did reach a singularity again, Would time reset? Could a new Big Bang occur, creating a new universe with a new flow of time? These are tantalizing questions, but current observations of dark energy suggest that a big crunch is unlikely in our universe's future. The most violent and dramatic end-of-time scenario is the Big Rip. This theory suggests that dark energy, the mysterious force accelerating the universe's expansion, could grow stronger over time. In this case, dark energy would not only push galaxies apart, but also stretch everything in the universe to its breaking point, including the very fabric of space-time. In the Big Rip, dark energy's force would increase to such a degree that it would begin to tear apart galaxy clusters, individual galaxies, and even solar systems. Ultimately, it would stretch and destroy stars, planets, and atoms themselves. The closer we get to the Big Rip, the faster and more destructive the expansion becomes. At the very end, even the smallest particles like electrons and quarks would be ripped apart, and space-time itself would unravel. The universe would reach a point of infinite expansion in a finite amount of time, meaning that time itself would cease to have any meaning. Like the Big Freeze, the Big Rip envisions an end to the universe. But in this case, time and space are violently torn apart, leaving nothing behind. One of the biggest questions facing modern cosmology and physics is whether time is a fundamental feature of the universe or an emergent property. In the classical view of physics, time is fundamental. It's woven into the very fabric of space-time and defines the order of events. But in certain interpretations of quantum mechanics, and in theories like loop quantum gravity, time is not a basic building block of reality, but an emergent phenomenon that arises from more fundamental processes. If time is emergent, it raises the intriguing possibility that time itself could end. In scenarios like the Big Freeze, time might lose all relevance as the universe reaches a state of thermodynamic equilibrium. Without change or events, the flow of time becomes meaningless, even if the universe continues to exist. In the Big Rip, time could be torn apart along with the fabric of space-time, bringing about an abrupt end to both time and space. These ideas challenge our everyday understanding of time, but they also open up new avenues for exploring the deepest mysteries of the universe. Could time, which began with the Big Bang, also have a finite end? This remains one of the great unanswered questions in physics. As we look to the future of time, it's impossible to ignore the role that black holes will play. Black holes are some of the most fascinating and mysterious objects in the universe, and they have a profound impact on how we think about time. In a way, black holes are time traps, regions where time behaves in ways that defy our intuition. A black hole forms when a massive star collapses under its own gravity, compressing all of its matter into a singularity, a point of infinite density. Surrounding the singularity is the event horizon, the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. One of the most mind-bending aspects of black holes is how they affect time. According to Einstein's theory of general relativity, the stronger the gravitational field, the more time slows down. Near a black hole, gravity is so strong that time for an outside observer would appear to nearly stop as an object approaches the event horizon. For someone falling into the black hole, time would continue normally from their perspective, but from the outside, they would appear to freeze in place at the event horizon, never actually falling in. This phenomenon is known as gravitational time dilation. Near the singularity of a black hole, time could, in theory, cease to exist altogether. The concept of time within a black hole remains one of the biggest challenges in theoretical physics, because it involves the breakdown of our understanding of both general relativity and quantum mechanics. As stars die and galaxies age, black holes will become more dominant in the universe. Over billions of years, as stars burn out and galaxies become inactive, black holes will be some of the last remaining structures in the cosmos. In the far future, supermassive black holes, which reside at the centers of galaxies, will be some of the last remaining bastions of matter. But even black holes are not eternal. In the 1970s, physicist Stephen Hawking proposed that black holes could slowly lose mass over time through a process now known as Hawking radiation. This radiation occurs when particle-antiparticle pairs form near the event horizon of a black hole. One particle falls into the black hole while the other escapes, effectively causing the black hole to lose a tiny amount of mass. Over incredibly long timescales, on the order of 10 to the power of 100 years, black holes will eventually evaporate completely, leaving behind nothing but radiation. When the last black holes evaporate, the universe will have entered its final stages. Without black holes, stars, or galaxies, the universe will be a cold, empty expanse, drifting toward the big freeze. In this final state, time as we understand it will have no events left to measure. The universe will have become a featureless expanse of particles in a state of maximum entropy. As we contemplate the distant future of the universe, we must also consider how time itself might behave as the universe approaches its end. Whether the universe ends in a big freeze, big rip, or some other scenario, time will be inextricably linked to the fate of matter and energy. If the universe continues expanding indefinitely, time will stretch alongside it. In a universe with no stars, no galaxies, and no black holes, time might become a meaningless concept, without any events to mark its passage. Time could continue indefinitely, but without any way to perceive or measure it. On the other hand, if the universe were to end in a dramatic collapse or tear, time could cease to exist entirely. In the case of the Big Rip, time and space might be ripped apart together, bringing an abrupt end to the universe and time itself. In a big crunch, time could reverse or fold in on itself as the universe collapses, leading to a singularity where time loses all meaning. In all of these scenarios, the future of time is deeply uncertain. What we do know is that time, like the universe, is dynamic and ever-changing. Its future is as mysterious as the universe's ultimate fate, and as we continue to explore the cosmos, we may yet uncover new insights into how time will behave as the universe approaches its end. As we reach the end of our exploration of the future of time, one thing is clear. The fate of the universe and the nature of time are inextricably linked, from the accelerated expansion driven by dark energy, to the possible fates of the universe, big freeze, big crunch, or big rip. Each scenario offers a different vision of how time might evolve. Black holes, the remnants of dead stars, serve as time traps, where time slows down or even stops near their event horizons. In the far future, as stars burn out and galaxies drift apart, black holes will dominate the cosmos until even they evaporate, leaving behind a universe devoid of matter and energy. In this final quiet stage of the universe, time may lose all meaning. Without events, without processes, Time as we experience it could cease to exist, stretching into an infinite, unchanging expanse. Alternatively, the universe could end in a violent collapse or tear, bringing an abrupt end to time and space together. The future of time is a mystery, but it is one that continues to captivate scientists and philosophers alike. As we peer into the farthest reaches of the cosmos and the deepest layers of time, we are reminded that time is both a fundamental part of our reality and an ever-evolving mystery. The story of time is not yet over, and as we continue to explore the universe, we may yet uncover new and profound insights into the nature of time itself. Time. It is woven into the fabric of our everyday lives, guiding our schedules, structuring our history, and helping us anticipate the future. Yet, as we've seen in previous chapters, time is not as simple or as straightforward as it seems. At the frontier of our understanding, philosophers, physicists, and thinkers grapple with fundamental questions about the nature of time itself. Is time truly real, or is it an illusion that stems from our limited perception? Could the past, present, and future all exist simultaneously? In this chapter, we will explore the most profound and challenging ideas about time, ideas that lie beyond the boundaries of what we currently understand. The question of what time is has long perplexed philosophers. Is time a real, tangible entity, or is it merely a construct of the human mind? Can we move forward and backward in time, or are we irrevocably bound to the present moment? Two of the most prominent philosophical views on the nature of time are eternalism and presentism. These theories offer starkly different answers to the question of what time really is and how it functions in our universe. Let's begin with eternalism, a theory often associated with the block universe model. According to eternalism, all moments in time, past, present and future, exist simultaneously, much like the pages of a book. Just as every page of the book exists at the same time, even though we only read one page at a time, eternalism suggests that the past, present and future are all equally real. From this perspective, time does not flow in the way we experience it. Instead, our perception of time as something that moves forward is simply a consequence of our limited perspective within the block universe. The idea of eternalism fits well with the theory of relativity, which shows that time is not an absolute or universally experienced phenomenon. Instead, time is relative, meaning that two observers in different states of motion may disagree on the order of events. In a sense, relativity suggests that time is not a river that carries us from the past to the future. It is more like a landscape that we traverse in different ways depending on our position and speed. In this block universe, every moment, whether it occurred millions of years ago or will happen in the distant future, is already laid out, waiting to be observed. Now let's consider presentism, the view that only the present moment exists. According to presentism, the past is no longer real, and the future has not yet come into existence. The present is all that exists, and it is constantly being renewed as each new moment replaces the last. In this view, time is like a flowing stream, with each moment being swept away into the past as soon as it occurs. Presentism aligns more closely with our everyday experience of time. We feel that the present is special, that it is the only moment we are actually living. The past is something we remember, and the future is something we anticipate. But neither seems as real or as immediate as the present. However, presentism faces challenges from modern physics. For example, the relativity of simultaneity, a key feature of Einstein's theory, suggests that different observers may disagree on what constitutes the present. If two people cannot agree on which events are happening right now, how can the present be the only thing that exists? Ultimately, the debate between eternalism and presentism strikes at the heart of the mystery of time. Is the flow of time an illusion created by our minds, or is the passage of time a fundamental feature of the universe? Philosophical debates about time are not limited to Western thought. Different cultures and civilizations have developed their own conceptions of time, which often reflect their worldview and cosmology. One of the most fascinating contrasts is the difference between cyclical time, prevalent in many Eastern traditions, and linear time, which dominates Western thinking. In Western thought, time is typically viewed as linear, a straight line that moves from the past through the present and into the future. This concept of time underpins much of Western religion, philosophy, and science. In Christianity, for instance, history is seen as unfolding according to a divine plan, moving from the creation of the world toward a final judgment and the end of time. Similarly, the scientific method relies on the assumption that events follow a linear progression of cause and effect, allowing us to predict the future based on the past. By contrast, many Eastern philosophies and religions view time as cyclical. In Hindu cosmology, for example, time is thought to move in great cycles known as yugas. Each yuga represents a different phase in the universe's history, and when one cycle ends, another begins. The idea of cyclical time is also present in Buddhism, where the concept of samsara refers to the endless cycle of birth, death, and rebirth. Rather than moving toward a single endpoint, time is seen as repeating itself in a never-ending loop. The contrast between these two conceptions of time, linear and cyclical, raises profound questions about the nature of reality. Is time a one-way street that leads us toward a final destination, or is it a continuous loop, constantly cycling through creation, destruction, and renewal? These cultural perspectives offer us different ways of thinking about the future and the meaning of time in our lives. As we move from philosophical debates to the cutting edge of modern science, the mysteries of time become even more complex. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, introduces new and bizarre ideas about time that challenge our classical understanding of reality. At the quantum level, time doesn't behave in the way we expect. In fact, some physicists argue that time might not even exist in the same way that it does at larger scales. In the realm of quantum mechanics, particles like electrons and photons don't follow the clear, predictable paths we see in everyday objects. Instead, they exist in a state of superposition, meaning they can be in multiple states or locations simultaneously. It's only when these particles are observed that they collapse into a definite state. This strange behavior has led to some perplexing questions about how time operates at the quantum level. In classical physics, time is seen as a continuous flow, a smooth progression from one moment to the next. but in quantum mechanics. Time may be more like a series of discrete moments or quantum events. These events are not necessarily tied to a universal clock ticking away in the background. Instead, time might emerge from the interactions between particles, rather than being a fundamental backdrop against which events occur. One of the most puzzling aspects of quantum mechanics is how particles can become entangled, a phenomenon in which two particles, no matter how far apart they are, remain connected in such a way that the state of one particle instantly affects the state of the other. This phenomenon, known as quantum entanglement, suggests that information can be transmitted across vast distances faster than the speed of light, seemingly violating our understanding of causality and the flow of time. Quantum entanglement raises profound questions about the nature of time and space. If two entangled particles can influence each other instantaneously, regardless of the distance between them, does that mean they exist outside the normal constraints of time? Some physicists have suggested that entanglement points to a deeper underlying reality, in which time and space are not fundamental, but rather emergent properties of a more complex, interconnected universe. One of the most intriguing implications of quantum entanglement is its potential role in quantum computing. Quantum computers, which are still in the early stages of development, use entangled particles to perform complex calculations at speeds far beyond the capabilities of classical computers. But what does this mean for our understanding of time? If entangled particles can communicate instantaneously, does that mean they exist in a realm beyond time? These questions are at the cutting edge of modern physics, and while we don't yet have definitive answers, they suggest that our understanding of time at the quantum level may be fundamentally different from the way we experience it in our everyday lives. One of the most popular speculative ideas about time, both in science fiction and in theoretical physics, is the possibility of time travel. Could we one day move backward or forward in time, much like we travel through space? In Einstein's theory of general relativity, time and space are intertwined in the fabric of space-time, and under certain extreme conditions, space-time can be curved or warped in such a way that time loops back on itself. These loops, known as closed time-like curves, theoretically allow for time travel. If you were to follow a closed time-like curve, you could return to a point in time before you left, essentially traveling backward through time. However, time travel introduces a host of paradoxes that challenge our understanding of causality. One of the most famous is the grandfather paradox, in which a time traveler goes back in time and prevents their own grandfather from meeting their grandmother, thereby preventing the time traveler's own birth. This creates a logical contradiction. If the time traveler was never born, how could they have traveled back in time in the first place? Some physicists argue that such paradoxes are evidence that time travel is impossible. Others suggest that time travel might be possible, but that the universe would somehow prevent paradoxes from occurring. One theory, known as the Novikov self-consistency principle, proposes that any actions taken by a time traveler would be self-consistent with the history of the universe. In other words, even if you try to change the past, your actions would be constrained in such a way that the timeline would remain consistent. Time travel remains a speculative and controversial topic in physics, but it continues to captivate our imaginations and inspire new ways of thinking about time. As we delve deeper into the mysteries of time, we must also consider its relationship to consciousness. Our perception of time is intimately tied to our awareness of ourselves and the world around us. But what if time, as we experience it, is merely an illusion? What if our perception of the passage of time is a product of the way our brains process information, rather than a reflection of objective reality? Some physicists, like Carlo Rovelli, have proposed that time might not exist at all, or at least not in the way we think it does. In his book The Order of Time, Rovelli argues that time is an emergent phenomenon, not a fundamental aspect of the universe. According to Rovelli, time emerges from the way systems interact with one another. At the most basic level, in the quantum world, there is no universal now, no past, and no future. Instead, time is a way of describing the relationships between events. In this view, the flow of time is a subjective experience created by our consciousness. Our brains are wired to perceive the world in terms of cause and effect, leading us to experience time as a linear progression. But at the deepest level of reality, time may not exist at all. The universe, according to this theory, is not a clockwork machine ticking away the moments, but a web of interconnected events, where the concept of time is a useful but ultimately artificial construct. Our understanding of time is shaped by the way our brains process information. Neuroscientists have found that our perception of time is closely linked to our attention, memory, and emotional state. When we are highly focused on a task, time seems to fly by. But when we are bored or waiting for something, time drags on. This suggests that our experience of time is not constant, but flexible, depending on our state of mind. Moreover, our sense of self, the continuity of our consciousness from one moment to the next, is deeply tied to our perception of time. Without memory, we would have no sense of the past. And without anticipation, we would have no sense of the future. Our experience of time is, in many ways, the experience of being conscious. But if time is an illusion, what does that mean for our sense of self? If time does not exist at the fundamental level of reality, does that mean that our consciousness, too, is an illusion? These are profound and unsettling questions, but they lie at the heart of the mystery of time. As we reach the limits of our understanding, the nature of time remains one of the most profound and challenging questions in both philosophy and physics. From the debate between eternalism and presentism to the bizarre world of quantum mechanics, time continues to defy easy explanations. Some physicists argue that time is a fundamental aspect of the universe, while others suggest that it is an emergent property or even an illusion created by our consciousness. As we explore these frontiers, one thing is clear. Time is not a simple, straightforward phenomenon. It is a complex and multifaceted concept that touches on the deepest mysteries of the universe and the nature of our own existence. Whether time is real or illusory, fundamental or emergent, it remains one of the most fascinating and elusive subjects in human thought. As we continue to push the boundaries of science and philosophy, we may yet uncover new insights into the true nature of time, and in doing so, reveal new truths about ourselves and the universe we inhabit. As we come to the end of our journey through the mysteries of time, we find ourselves once again in the present moment. It's where we started, and now, after travelling from the birth of the universe to its possible future demise, from the smallest quantum scales to the vastness of galaxies, we return here. In this instant, right here, right now, you exist. The clock ticks softly in the background, reminding you of time's steady march forward. Yet, as we've discovered, time is anything but simple. Take a deep breath and consider. At this very moment, your life is unfolding. Every decision you've ever made has led to this point. The present feels real, tangible, something you can hold on to, if only for a fleeting second. You're surrounded by familiar sights and sounds, grounded in a reality that seems governed by time. But as we've explored throughout this documentary, the nature of time itself is elusive, stretching beyond the bounds of our perception, slipping through our fingers just as we try to grasp it. When we began this journey, we asked, what is now? It seemed like such a simple question, yet the answers have proven anything but straightforward. We've delved into the earliest moments of the universe, where time itself began to unfold from the singularity of the Big Bang. We've travelled forward through cosmic inflation, the formation of galaxies, the life and death of stars, and the relentless expansion of the universe. We've touched upon the deepest questions of philosophy, whether time is real or an illusion, whether the past, present and future all exist simultaneously, or if only the present moment is truly real. At each step, we've seen how time influences everything, from the microscopic dance of particles to the grand choreography of galaxies. It binds the smallest quantum fluctuations with the most massive black holes, and yet, at its core, time remains a profound mystery. As we stand at the edge of this exploration, we are left with one final question. What does time mean to us? Time is the rhythm of our lives. It is the silent backdrop to our joys and sorrows, the stage upon which every moment of our existence plays out. We measure time in the ticking of clocks, the passing of days, the turning of seasons. We celebrate its passage with birthdays and anniversaries, and we mourn it when we lose loved ones to its inevitable advance. Yet, as we've learned, time may not be as straightforward as it appears. From the perspective of physics, time is not a single, universal current flowing forward, carrying all of us at the same speed. Rather, it is relative, stretching, bending and warping, depending on where you are in the universe and how fast you're moving. At the quantum level, time may not even exist in the way we experience it. It might emerge from the interactions of particles, or it might be something entirely different, something we do not yet fully understand. So, what does this mean for us as individuals living our lives in the present moment? Perhaps time is a thread that connects all of existence. It links us to the stars that died long ago, whose remnants formed the atoms in our bodies as it ties us to the future. to the distant descendants who will one day look back at our time as ancient history. Time connects every moment of our lives, from our earliest memories to our hopes for the future. And yet, it eludes full comprehension. We are passengers on this train called time, moving through moments, each of us creating our own version of now. For every individual, this now is unique. The present moment, for you, feels special because it is your moment. But in the grand scheme of things, time might be something far more profound, a concept that transcends our individual experience and connects all of reality. Time, as we've discovered, is a force that governs the universe, but it is also deeply personal. It shapes who we are, how we live, and how we experience the world around us. As we move forward, it will continue to guide us, even as we strive to understand its deepest mysteries. So, as you sit here in this moment, your moment, take a final pause to reflect on the journey we've taken. We've explored the origins of time, the future of time, and the nature of time. We've looked at it from every angle, and yet it remains one of the greatest puzzles of existence. Perhaps that is what makes time so beautiful. It is something we live with every day, but it is also something that will continue to inspire wonder and curiosity for generations to come. In the end, time is not just a ticking clock or a page on the calendar. It is the story of the universe, written in every second that passes, every star that burns out, and every life that unfolds. Time is our constant companion, and though we may never fully understand it, we are forever shaped by it. And now, as the present moment slips into the past once more, we are left with a simple, timeless truth. Time is the greatest mystery of all.